C and roll. Get that command. Anframma. Yes, it's time. Are we waiting for someone?
Hello, someone. Silence. No. Okay, what's in my program for today? Earth fault protection. I would like to start with earth fault protection. Earth fault protection. Earth fault. It's a special group of protection using zero sequence components. And now, capital question. What is zero sequence? EFP Earth fault protection or in Latvian ZSA Zemes slēguma aizsardzība. Zeme means earth, slēgums means fault un A aizsardzība ir protection. Zemes slēguma aizsardzība. Tad, jautājums. Question, what is this? What means zero sequence current? What means use zero sequence component? Can you tell me what is the technique of symmetrical components? What is silence? Did we have a course in previous semester on net calculus? Yeah. And did I explain technique of symmetrical components? Yeah, I can find the video. So why it's so quiet here when I'm asking about zero sequence component? What's behind idea of symmetrical components? What is silence? Oh my God, where am I? Fortescue. This guy invented, started with the idea. Real developers were two persons, Fagners and Evans. But Fortescue started. Idea of Fortescue. You have non-symmetrical network. you have non-symmetrical polyphase network. You have A, B, C voltages, or you have A, B, C current, ABC or red, blue, yellow.
Yeah.
A, B, C, same, L, B, Y, O, L is T somewhere. L1, L2, L3. So you have triplet non-symmetrical network. It will be torment of pain to calculate it directly, because you will need to take into account what? Transformer. In case of transformer, you need to take into account free mutual inductance at primary side, free mutual inductance on a secondary side, 3 plus 3 plus 1, 2, 3 plus 3 by 3 matrix of mutual inductance side by side. It's easier to go and hang on the nearest tree. The same thing with the line. For each line you need to take into account magnetic couplings between phases. So idea was to find linear transform eliminating most of this mutual coupling. It is possible. Idea is they live here. See these two guys. One. They proved in 1982, sorry, it's published in 1982, idea of theoretic base for transform eliminating mutual components in resistance matrix. What kind of transform it should be? But first was found by Fortescue. Actually, rethinking idea of Blundel's double reaction from electrical machines. So what's the idea of Fortescue transform? Idea is what you can substitute A, B, C. Complex polyphase network, unsymmetrical, with a set of symmetrical components, symmetrical networks, only huge covenant. Your network should be linear. What means linear network? Current always proportional to voltage. This resistance is linear. non-linear. So, in case your network is linear, you can substitute A, B, C to third P or 120 elliptical degrees with the system of direct sequence plus, what's the name of second sequence? A, C, B, again 230. This one is direct, second marked with 2 is a negative on opposed sequence. Ideal network with ideal generator and ideal symmetrical load. This one is negative. Generator rotates in opposite direction. And A, B, C. Special case. All three phases are connected together. A, B, C. And powered by single phase generator. Imaginary network called zero sequence network. This needed to represent ground current or current in neutral wire. So idea of Fortescue transform is substitution of original non-symmetrical polyphase system with set. In case of three-phase network, it will be free. Actually, for M-phase network, there will be come on, M-1 symmetrical stars with all possible phase sequence plus 1, 0. Idea of symmetrical components. What is idea of symmetrical components? Substitute real complex with set of ideal. Where the dog is digging? Why it's working? Because in case of symmetrical system A, B, C, sum of components will be what? 0. Influence from mutual inductances will be 0 because you will have 1, 2, 3. Idea started with elimination, knowing what in symmetrical network face-to-face mutual inductance can be neglected because their influence forms the same thing around this triangle. Meaning what? Total influence is neglectable because sum of induced voltages real will be 0. This is true only for symmetrical star. Actually, if you once would decide to check it, you will need to go into octagonalization of resistance matrix. Actually, you will start from this paper, component transformation and gain values analysis defines the relations. This is where you will start if you want to go deep into this theory. There are known transformations like Fortescue, current power, Clark, Wedge-Paul, and unnamed, only existing in theory. But what I'm willing to write? Yeah, I'm willing to write Fortescue transformation. UA direct sequence, UA negative sequence, U0. 1/3 1A squared 1A squared A 1 1 1 multiplied by here is transformation formula for voltage, or U in sequence equals to 1/3 transform matrix of Kierkegaard, U in phase coordinates. Same is true for currents. In phase coordinates. True for currents. Something familiar, no? Semester distance when I wrote it, and you always should remember it. I already forgot. Okay, what means A? A specific thing. A is A power 2/3 P, meaning, its meaning is, if this is X, rotated forward 120 degrees will be AX. It's a rotation operator. A squared is A power minus your 2/3 P. Yeah, here it is. Now, what about, for case inverse transform, if for example you would like to get currents from symmetrical components, A, B, C equals to 1, 1, 1, A squared A sequence, a negative sequence, and I0. Yeah. Here it is. So current in phase coordinates equals to inverse transform matrix current in sequence coordinates. Why am I repeating this? Now, let's say I have source, grounded, neutral, okay, I can draw Holmgren schematics. Current, current, current. A phase, B phase, C phase transformer. What flows here? Neutral via relay. What this relay will see? Ideas? What flows through this relay? B phase and wait, where is my red? What will we see? Flowing through this relay. For example, here is 1 megawatt of power. Voltage 110 kilovolts. 1, not enough. 11 megawatts of power. What will we see? if I plug ammeter here, what will I see? I'll take my measurement tool. What will I see? Yeah, it's a current meter. Appears. I'm not sure. Somewhere from VV2 error. Copper rectifier. So what will I see? How many amps? 11 megawatts. Ideas. $110 kilovolts network, 11 megawatts, and correct answer is look here, symmetrical. Symmetrical. You have delta connection. What can you see? Eh? What flows here? Current, which is vectorial sum of B, A, and C currents. What will I see? Huh? Zero. Of course, in symmetrical regime, it's zero. Actually, here flows triple zero sequence current. In case of symmetrical regime, it will be zero. And in case of ground fault, it will be full current of. If we have fault current here, triple I0, as I showed, we will get fault current. Why I'm wasting time on this schematic? Huh? What's interesting here? We have no signal in load regime, yeah, zero signal, and full fault current in case of fault regime. This means what? What we can get very sensitive and robust protection. Yeah? Yes. So Earth fault protection relies on zero sequence current, and it's highly sensitive. For many years it was instituted by law as a main protection of one Earth and ground high voltage network. Now it's also mandatory, but it's mandatory as a backup primary distance. But it's still very reliable. Only small problem, as I draw it, yeah, it's fine, but it isn't easy to find a radial kind of connection in such networks. In person, I knew only one line in the region where power is supplied from one side. All other cases are double fed or power from both sides. That means what this protection will require what? Direction. It should be polarized or directed. If we deal with double side fed network, we need direction. Now, what kind of schematics you need to employ to analyze your net? Let's say you have source, transformer, V1, circuit breaker, V2, source. Something like this. Here comes the power. And Earth fault at a distance of alpha. Fine? Delta, transformer 1, transformer 2. I need 3-second schematics. Schematics of direct sequence. One. Of V2. 1 of ground for direct sequence. This is schematic of direct sequence. Here I'm showing FP or P or F. What is P or F? Place of fault. Do you understand how I created this? It's an A phase of my network. I took one phase because it's symmetrical. For negative sequence, this will be connection, it's N2. This is N1. 1 minus alpha. My second transformer, common ground, neutral for negative sequence. This is negative sequence. And now, important part. Since I have star delta transformers, try to understand this thing. In zero sequence network, I should analyze transformer like all these terminals are connected together and power source attached between star center and these connected terminals. What will happen here on primary side on delta? Normal. We have sum of free vectors and no circulating current. Yeah? Otherwise, it would burn. But it's not burning. I can switch it on. Okay? Nothing works without the power. Nothing goes because there is virtually no circulating current in symmetrical regime. But in zero sequence regime, current will circulate. So delta connection forms a short circuit for the zero sequence. Direct. Zero sequence resistance of the first one, if not known exactly, it's approximately 3 times higher than the zero sequence resistance of overhead line, approximately 3 times higher than the direct sequence. Zero sequence. Here can be connection. 1 minus of zero sequence resistance of my second line, and all this comes together to the point N0, and if there is transient resistance, transient resistance, it should go triple here. Current flows in a direct sequence in the place of fault. Here is your schematic. Now, where my relays see? I can have A, B, C, and D relays. This is place for A. Here sits B. And yeah, a bit more space. B, C, and here is relays D. This is voltage for B and C. This is voltage for A. We are interested in B and C. Current. How? Here is zero sequence voltage. This voltmeter measures current zero sequence current through relays. You see, for B, current will be like this. For C, if relay is set to have start toward buses, current inflows in case of internal fault. But here is one moment with voltage. What kind of voltage do see my relays? There are two different, how to say, sets of relays. Relays what use U0, actually 000, some from voltage transformer, or relays using minus U0. If A phase voltage is plus, where zero sequence voltage looks? For example, here, this is zero sequence voltage A phase. It looks like this. Which way this voltage looks? If this is ground, here is the ground point. Which way looks this voltage? This one, orange. This is my zero sequence voltage. Which way it looks? Down. At a point of fault, sum of voltages is zero. So here, at the point of fault, direct sequence voltage equals to sum of zero and negative sequence voltage. Negative will be smaller because resistance of this network is approximately 3 times higher than this network. Your zero sequence voltage looks down. Current, where the current will be? For typical network. Current is approximately 70 degrees and lagging. Now, careful. Here is your zero sequence voltage. Current goes same way. There are two types of relays. T moment is direction. Can I erase this? Will you remember something? Here is star for voltage and here is star for your voltage. Most important thing with this kind of protection is direction function. It's so, how to say, threatening. Is it so complex? Really? Very simple schematics. It's a simple schematics. So, what I'm talking, your function, your direction. You need to separate internal faults from external. One plus Idea 1. Voltage of relay. Assuming current from relay approximately 70. What have I selected as a voltage for my relay? U0 or minus U0? If I assuming 70 degree. Minus U0. This one is for minus U0. Now, remember Earth's fault protection, this direction function is not compatible with line-to-line fault protection. It's not compatible with overcurrent protection. Statistics, old, it's quite old analysis, but it's good analysis. Suggested to have maximum sensitivity angle this way is better. 63 plus minus 5 degrees. It's an angle of maximum sensitivity for Earth's fault relays. For 110. For 300 and higher, it goes towards 8, but this will work. And go, no go line. This is go, no go. And all internal faults will be here. Polarizing voltage minus U0. In case of U0, it will be mirrored. This is area of internal faults. Faults in line V2. For case of faults in line V1, current voltage remains the same, but current will flow this way. Actually, this is area of external faults. Old school used direct border. Sometimes more conservative approach is used, adding here for safe some 20, 30 degrees. It's not devastating, it's just for additional safety. Here is set up for the Earth fault protection for grounded networks. Such kind of relays are not compatible with everything else. Only for this kind of application. Cannot be used in any other protection, will fail. Maximum sensitivity angle 63, 65. Old standard 63 plus minus 5. It's for 110 kilovolts network. Not usable for distribution network. Now, how settings are created. This protection works very well, but you need to do settings correctly. Maybe I okay, I can two charts. A1, C1 instant zones. A2, A3 delayed zones. 1/2 of second, T1 second, T1 half of seconds. A, D direction, here from the opposite side, D1, B1, B2, D2 and D3. Structure of time delays, same as we saw in overcurrent protection. Same structure, the same. but operating values are not the same. For the first zone, Earth's fold at the end of the line marked external current. Trip current, right? For the first zone, and here one moment, I need to point its finger. There are relays programmable for I0 and relays programmable for triple I0. Actual from transform current sensors will came triple I0. All the relays were programmed for triple I0. Modern digital relays, open relays manual, it's programmable for I0 or triple. Measured value is triple I0. Triple zero sequence current. But there are relays where zero sequence current should be set. Schematics factor. 1, safety. 1.1. No. Return, nothing. Fault 1, so it's E0 marks external. Transformer ratio. For the instant zone, no return factor is needed. Only ratio of transformer, but again, I will write it in the I0 or triple I0. Be careful with manual. From transformer we came triple. This is for instant zone. For case, trip time is 0. For delayed zones, trip current. For delayed zones, is trip current for A2, for example, will be safety coefficient 1.1 multiplied by square E max external. I can use this NL. What's mean NL? Next line. Take max external current, fault current, but for the next line, it's for this zone. It's coordinates with the end of next protection instant zone. Here should be 10% margin. To do so, you take max external, but for the next line. Multiply it by square of safety factor. Here should be transformer ratio and return factor of your protection. For modern relay, it will be 995, 0.96, so 5-6% hysteresis. Fine. What with the last zone? Last zones for ordinary overcurrent. Here, this part resembles ordinary overcurrent protection. For the last zones is a huge difference. Last zones can be made very sensitive. The only limiting is what? Zero sequence current and normal mode. In theory, it should be zero. In real life, you will see non-balanced current with two sources. Source 1, error of your current transformers. Source 2, network, non-symmetry. If you take a look on the network, distance between wire and ground are different for phase. So capacity is not uniform. This meaning that in normal operation regime, you will see some current. The network isn't absolutely uniform. So for last zones, like A3, driving factor is non-balanced. Here, trip current should be safety factor divided by transformer and multiplied by non-balanced current max. Old books recommended 1/10 of the external three-phase fault current. No, it's not based well. It's written from idea of what fault protection, line to line fault protection will not operate. It's not the best idea. Your non-balanced current max is 1/10 of EOR. This is good. 1/10 of max possible load current. Your protection will be very sensitive. Really. It's more sensitive than the distance protection. That's why here we have problem. Earth fault with trees, with high internal resistance. Current in case of such fault is so small that distance protection cannot operate safely. It's not a good thing to deal with. So it's a mandatory here in our practice. It's mandatory to have a sensitive zero sequence protection. I may draw schematics of such protection. Yes, let's say. Triple I0. From voltage transformers, this is open triangle triple O 0. One drawing where the signals can come from. And now logic of protection. Triple I 0. Instant zone. This is instant. Okay, it's two. I can draw two delayed zones. Or receive 000 sequence current. Fine. Next. Angle function. These all are current. Realize this last one is an angle function. That's fine. Time delay function. Indication trip of any activates output pulse delay relay a function. This is output pulse format, and via one we will get signal to terminate connection. Here is block schematic of earth fault protection. Set of current relays, one angle relay and function, and set of time delays. Here stands last operated electromechanical earth fault protection in Latvia. This one was the last, was the commissioned last one. Power direction, zero sequence direction, 1, 2, 3 current relays. These are indication for first, for instant, for second, and for third one. And here set of time relays. It had one relay for each zone. First zone also can be delayed. Now, small problems. It's a bit strange, but it had opposite numbering. This one is for instant, this one for first delayed, and this one for more sensitive. Strangely, it has opposite numbering. Now, one small problem. It's a problem of sensitivity. And maybe, I shouldn't erase it. First moment, such kind of protection, in case, what to do in case switch on fault. There is virtual no problem of zero sequence under voltage. Virtual no, it only, see, I need to draw one interesting diagram. For example, I have transformer, line, transformer, source, source. Here is my earth fault. How power of sequence looks like. Direct sequence. With direct sequence, I will see power distribution like this. It's for active power. Lowest point is at the fault. This is for direct sequence. Zero sequence, powers from direct. This is zero, let's say active power and zero sequence. It's powered from the fault place. So, meaning what closer the fault place is towards relay, the higher power relay will see. That means what there is virtual no sensitivity problem with the close fault. Sensitivity problem goes this far from relay when my protection operates as a backup. Yes, there can be a rare case of sensitivity problem if this transformer is huge. Because in zero sequence, let's say that line direct sequence, direct sequence, this is U0 at a fault place. Zero sequence current or relay. If transformer is huge, this resistance will be small and observed voltage may be tiny, but it should be extremely huge transformer. Anyway, in case of close fault, you will have voltage. So sensitivity problem goes far. This kind of protection usually do not suffer from sensitivity problem in case of near fault. The closer fault, the higher signal. Anyway, it's a good practice to predict switch on fault condition. Old relays had in old design from okay 1 delta T my switch, it's a normal closed time relay. They had delayed return circuit like this. It's a fast, how to say, fast track circuit active only for half of a second after circuit breaker is switched off. Idea, it's a fast circuit activated for approximately usually 1 second. Not activated, it's activated when circuit breaker is off and remains active for 1 second after switch on. This is speed up before for switch on fault condition to make this protection operate instantly. It was done for because this was a basic protection, main protection, better name it main protection. In modern designs, such bypass circuit is considered not so good solution, and non-directed zero sequence protection is better solution. Non-directed has its own and it has a zero greater, it's a zero, and it has indication. It's non-directed protection branch, active for 1 second, remains active for 1 second after switch is on. Non-directed zero sequence protection. Such brand is better because you can select time delay independently. This is for switch on fault operation. Now where you can face problems. When you can face problems, you need to coordinate zero sequence resistance of your network. Meaning, what if you have think like double transformer substations, in the line. To prevent false operation of your zero sequence, you need to maintain constant resistance of the neutral. This transformer, normal, are able to withstand 1 degree lower, 35 kilovolts voltage in the neutral. So, in normal mode, spark discharge, if this is 110 kilovolt network, this will be for 45 kilovolts. Spark discharge. And only one of the disconnectors is on. Zero sequence resistance should remain constant. One transformer operates or two, only one neutral is grounded. You switch the second one on only connected transformer to the network or disconnected from the network. Other time, only one neutral should be grounded. It's moment number one. Moment number two, important. You have parallel lines. Remember, they are coupled with model inductance. Earth's fault here causes a zero sequence. This mutual inductance is real, accountable in zero sequence schematic. Current will circulate in disconnected and grounded line. You switch the second line off for repair, but in case of fault there will be a current. This appears like reduction in observable zero sequence resistance of this line. You need, it's your obligation, you need to recalculate settings, and before this line is switched off, you need to replace settings in these relays for so-called repair set. You need to recalculate settings for your relays. Because in repair mode, zero sequence of your line will be less, starting from 15 and ending with 30, maybe even by 1/3. Recalculate settings of your relays. Also, it's not so drastic, but if you have let's say here is external fault, I0 I0 in this case you will see in parallel line resistance greater. Remember, check it for your sensitivity. Maybe you may observe so-called zone shift. This case, it's for knowledge. When you calculate settings, calculate it for full. But here, in first case, you mandatory need to create a second set and put a second set for time of repair work. Or it will be, it can operate non-selectively. In case of external fault. Yeah, time is off. Questions?